What if some of the most accurate astronomical calculations in history were made not with telescopes or supercomputers, but with clay, reeds, and the night sky, asterisk. We live in a world of precision, atomic clocks, space telescopes, orbital mechanics, all of it timed to perfection. But over 2,000 years ago, in the cradle of civilization, a man named Kiddinu measured time and the movement of the moon with such startling accuracy that modern science is still catching up to the implications. His name is barely known today. Yet in the ancient world of Babylon, he may have been something like a modern computer of his time, a man who read the stars and carved their stories into stone. This is not just the story of one astronomer. It's the story of how humans first tamed time. To understand Kiddinu, we must return to Babylon, not just a city, but a civilization. By the time Kiddinu was born, sometime around 400 BCE, Babylon was already ancient. For centuries, its priest scribes had observed the heavens from atop ziggurats, those towering step temples that rose like staircases toward the gods. The sky was not a place of wonder alone, it was a calendar, a clock, a divine manuscript. For the Babylonians, astronomy was not a hobby. It was the core of royal power, agriculture, and religion. The gods spoke through eclipses. Kings reigned or fell with omens traced in Jupiter's path. Amid this cosmological machinery emerged a scholar whose name would echo through tablets and time, Kiddinu, or Kiddinu. Kiddinu's most celebrated contribution was perhaps the introduction of the Babylonian lunar theory, including what would become known as the System B, a remarkably precise model to predict lunar and solar phenomena. He determined the synodic month, the time between full moons, to be 29.530614 days. Modern science puts that number at 29.530588. A difference of just a fraction of a second. How did he do it? Not by telescopes. Not even by lenses. But by generations of meticulous observation, and the mathematical modeling of celestial cycles with zigzag functions and arithmetic sequences. It wasn't geometry, it was pure arithmetic astronomy. The kind that could predict eclipses centuries in advance. He didn't merely observe the moon. He tamed its rhythm, like a musician tuning an eternal metronome. The Babylonian astronomers kept astronomical diaries, daily logs of planetary motion, weather, river levels, even commodity prices. It was a civilization addicted to recording. Among these texts lies the possible signature of Kiddinu's genius, tablets from Uruk and Babylon that contain System B, a revolutionary method of lunar prediction, and potentially the first recorded use of a 365-day year based on solar-lunar reconciling. Some scholars believe Kiddinu was the originator of the sidereal year length, the time Earth takes to orbit the Sun, relative to the stars. Their estimate, 365.2565 days. Modern estimate, 365.25636. The difference, so minuscule, it would take thousands of years to accumulate a day's error. We don't know for sure if every line was written by Kiddinu. But the consistency, precision, and shift in astronomical modeling suggest a mastermind or a master teacher at the heart of it all. Though not a cartographer in the modern sense, Kiddinu's work mapped time and space in a way that would inspire centuries of thinkers. His system was part of a larger Babylonian tradition that understood the heavens as a grid, divided into degrees, ecliptic zones, and rising signs. This celestial ordering influenced Greek astronomy and ultimately Western cartography. Hipparchus, the Greek astronomer who introduced trigonometry to celestial models, likely had access to Babylonian data, possibly even Kiddinu's. He would use this knowledge to invent latitude and longitude, transforming how the Earth itself was measured. In this way, Kiddinu's lunar algorithms weren't just scientific. They were cartographic, laying the groundwork for measuring the heavens and the Earth in tandem. So when we talk about the history of mapping, we must go beyond Ptolemy and Mercator, and return to the reeds and tablets of Mesopotamia. Kiddinu never had a biography. His story survives through the silent testimony of stone, numbers, symbols, marks pressed into clay. There are no surviving letters, no portraits, no ziggurat named in his honor. But sometimes, precision is the loudest echo. His models influenced generations of astronomers, not only Greeks like Hipparchus and Ptolemy, but later Islamic and European scholars who inherited the structure of timekeeping through Babylonian foundations. And in a poetic twist, the modern calendar, the ephemerides used by NASA, and the software that guides telescopes still echo with numbers Kiddinu may have calculated over 2,300 years ago. What does it take to measure the moon, to the second, without metal instruments, without lenses, without even the concept of zero? This was the world Kiddinu inhabited, a cosmos without clocks, but not without time. A sky without sextants, but not without structure. He worked not with gears or glass but with memory, math, and method. To us, the moon's orbit is a number fed into a silicon chip, updated by radio signals from atomic clocks. But for Kiddinu, every observation was a ritual of patience. Each phase noted by eye. Every eclipse etched in clay, across decades, across generations. No telescope. No calculator. No decimal system. Just the sky, and the will to listen to it. He wasn't merely studying astronomy, he was inventing it as a system. Today, NASA predicts eclipses with satellite precision, using ephemerides built from relativity, supercomputers, and laser-mapped lunar topography. But when scientists overlaid modern moon models with Kiddinu's System B, something astonishing appeared: they matched. Nearly beat for beat. Error? Just seconds, across thousands of years. The very same math that once guided harvest festivals and temple rituals, now guides lunar landers, tidal models, and satellite trajectories. And in that moment, the clay dissolves into code. Not as a relic, but as a living thread connecting the earliest astronomers to the spacefarers of today. Kiddinu didn't have tools. He was the tool, a human instrument calibrated by decades of devotion. And his precision endures, not in monuments, but in mathematics. Kiddinu measured the moon with a whispering reed and a sky full of stars. In the story of science, he is one of those rare figures who didn't just look up, he listened to the sky. Because the heavens were not just his inspiration. They were his canvas.